I'm Ken Armijo. I work primarily in concentrating solar power. I was asked to basically take the latest research in concentrating solar power and give a presentation. That would probably take me about 3 hours and I still wouldn't cover it all. So I'm going to do my best. So for those that, just as a refresher, concentrating solar power, you have a solar tower where you have a receiver fluid like molten salts or sodium, or particle systems, which I'll talk about in a second, where you store that thermal energy. Presently with Gen 2 systems, it's about 6 hours of thermal energy storage, put into a power block, either steam or supercritical CO2, and you can produce power in a power block. Presently in the world, there's a number of Gen 2 CSP, so not nuclear, but Gen 2 CSP plants that have thermal energy storage, use molten salt and nitrate, so the solar salt, sodium nitrate, potassium nitrate, and there's functional systems right now in operation. The Department of Energy has Solar Energy Technology Office, SETO, which I'll use that acronym a bit, has been funding a number of different projects, and also the development of codes and standards, such as the API codes and standards, looking at salt tanks, looking at ASME materials, such as code qualifying Haynes 282 recently, and now they're looking at like Haynes 120, I think. And also looking at weldments and other projects, also to reduce the levelized cost of electricity and levelized cost of heat for different nickel-based alloys that are in communication with salt. So that gets into thermal fluids and looking at solar fuels for making hydrogen, ammonia, and even calcination processes for cement, which you have to facilitate above 900 Celsius. So there's a lot of interest in taking these molten salts up to very high temperatures. These are a number of projects funded by the Solar Energy Technology Office for molten salts. Funded with Sandia, NREL, and others, looking at different types of technologies, which I believe have a lot of crossover to nuclear and MSR technologies, especially when we get into materials compatibility. So I think there's a lot of cross-pollination. I know that Kevin, Rob, and I have talked over the years that we find from both groups. 4 years ago, the Department of Energy SETO office funded what's called the Gen 3 program. There were 3 pathways: the gas pathway with supercritical CO2 working with Brayton Energy, EcoGen, SWERI, and then you had the liquid pathway where we were looking at advanced chloride salts at 720 degrees Celsius, sodium in the receiver at 740 degrees Celsius, with thermal energy storage times going up to about 12 to 16 hours with discharge. We actually designed a pilot scale system that was 2 megawatts on our solar tower facility, and working with our partners in Australia, in ASTRI, working with companies that already have sodium in the receiver systems in a commercial level, and then working with the salt community in CSP, such as the Crescent Dunes facility that you see here with nitrates, looking to upgrade everything to advanced chloride salts, again, between 720 and 740 degrees Celsius. There are key challenges that we found in solar that's been discussed already as part of this workshop and in this community, where we've looked at corrosion challenges. We've had a lot of challenges working with stainless steels to drop the cost from using nickel-based alloys, but you have a lot of problems with chrome, nickel, and iron just leaching out and then depositing in places you don't want. Plus, you have reduction issues with magnesium chloride, which form mag oxide, which can have a Rockwell hardness 1/10 of diamond and just eating up your impellers, which we also found. And also you have HCl that forms. So big challenges that we find from a thermal hydraulics perspective in CSP that also are obviously evident in nuclear energy. Freeze and leak protection is a big challenge that we also found. Nitrate salts tend to volumetrically expand with temperature about maybe 3 to 5%. Chlorides, we found volumetrically expand as high as 27%. So it can break your welds if you don't uniformly thaw your systems. The veins within a pump can also break down, especially near the bowl assemblies. And so there's a lot of challenges that we found with the salts. In addition, we also find when we add the magnesium chloride, we can get very high vapor pressures as you go up in temperature. So when we're interested in chlorides, because they don't decompose like nitrates at 600 Celsius. But there are penalties as you go up and keep going up in temperature, say for our hydrogen and solar fuels work, you start to get very high vapor pressures. Again, we talked about the presence of HCl potentially also in our systems. So we've been doing a lot of work in monitoring and sensors, working also in parallel with the nuclear energy communities, such as Nathaniel Hoyt with chemistry corrosion control sensors and other sensors that can monitor vapor. Also working with companies like Sporian Microsystems who have pressure and more accurate pressure and flow sensors that operate well and accurately at 720 degrees Celsius, helping us to understand some of the key challenges. And of course, there's been a lot of techno-economic analysis looking at levelized cost of electricity in this space. Part of the work in the solar community is looking also at thermomechanical derated strength. So right here, you see the ASME boiler pressure vessel code. You basically see the drop off in thermomechanical strength and looking at new materials, again, that have been code qualified, such as Haynes 282. But one of the things I will point out that the DOE SETO did fund was they call it the Salt Chloride Consortium, because they formed this community amongst various laboratories, because when you look at corrosion data for different materials, you'll start to see that the data is kind of all over the map in some ways, because there's about 4 years ago, we found that there were a lot of inconsistencies, like crucible materials were not all the same. Some people were using Haynes 230, some were using ceramics like aluminum oxide. So there was a lot of challenge. And over the last 3 to 4 years, there's been a lot of work between like Oak Ridge, NREL, and Sandia to help standardize some of the testing, at least in the solar community. This is the National Solar Thermal Test Facility at Sandia National Labs. So again, we do a lot of solarized testing. We work in aerospace between temperatures of up to 3,000 degrees Celsius for reentry and hypersonics, but we also do a lot of high temperature systems. We've had salt receivers on the top of the solar tower. We've had sodium receivers at the top of the solar tower, and where we tested temperatures in nitrates up to about 585 Celsius. But also present here, we have one of the world's largest industrial scale test loops, which I'll talk about in a second. But we also test a lot of sodium systems and falling particle receiver systems. That was what the Solar Energy Technology Office finally funded, was the particle pathway, where you can we've tested particle temperatures with the second tower that's being built and other falling particle receivers up to 1,400 degrees Celsius. So there's a lot of material challenges. We also have 2 supercritical carbon dioxide power blocks at our facility to actually produce power on site. The big thing I wanted to also point out about our facility is the molten salt test loop. This loop basically has a 600 gallon per minute salt pump. It has an 8,000 gallon tank full of nitrate salt. And about 8 years ago, we had a power outage, and now the salt is all frozen in the tank that's subgrade. The U.S. Department of Energy, the DOE SETO, has funded a forensic study happening right now, and we are looking to get funded for phase 2 to actually restart the system. It can go up to about 600 psi, 585 Celsius, but again, it's 6-inch inner diameter piping, so you can really look at industrial scale equipment in a pretty configurable loop. One of the things I'm highlighted in red is that in order to get phase 2 funding, we need to get users. So all of you out there that are interested in testing your pumps, valves, sensors, different components at an industrial scale, we really would like to have you come and use our facility. And I put my information right here in case you're interested, because again, SETO is requiring users in FY24 and FY25 in order to fund the restart. I mentioned that it has 3 different loops. We have flow control valves. We have various sensors. Again, at very large scales, there's a lot of different challenges that you get versus a 2-inch piping loop. There's a lot of pressure gradients. There's thermal gradients. You get thermal expansion that happens a little bit differently, which we found. And so we're also even considering the use of nitrous oxide, something also our collaborators at DLR, the German Aerospace Corporation, have found that nitrate salts can be boosted to 640 degrees Celsius in terms of decomposition temperature. particular when you add nitrous oxide as an Ullage gas. So that's also something we're considering adding to this system. We've been doing a lot of materials testing in bulk salt in our salt pots, where we're looking at a variety of alloys. We've been looking at compressed materials where we can look at gaskets and seals and seeing if salt penetrates through. We have static valve actuation test systems. And what's nice about this salt pot test system is we can test 33 coupons at the same time. So we can, or individual coupons, but we can also see that dynamic of ion mobilization and test coatings. We've been working with companies like Powdermet, Liquid Metal Holdings, to not only create corrosion barriers, but also to create ionization mobilization barriers too. So you're not leaching these things out. And you have an order of magnitude cost difference when you're using stainless steels versus Inconel and nickel. So this has been pretty useful for a lot of our work. And in nuclear energy, we've been working with RIA's refractory high entropy alloys work up to 980 degrees Celsius. So we've been looking at these very high temperatures because you look at thermal excursions in nuclear systems, it's important to understand how these systems can perform in terms of their materials. We've also been able to assess these phenomena like which we call whiskers, where you get this mobilization of nickel and then it reprecipitates at the I don't know if there's a laser. It can reprecipitate at the interface between the liquid and the vapor space. This has been something of interest lately when you're looking at bulk salt test systems. Again, we're looking at penetration of the salt. These sorts of things we found challenging when we're looking at gaskets and seals. We've been working with companies like Flexitelic to develop spiral wound gaskets. So instead of all welded connections that you have in molten salt systems, we can actually put flanges that are actually leak proof. And I'll talk about that in a second. One of the interesting finds that we're writing like 5 journal papers in the next few months is we've been looking at tensile strength challenges. There's this process of sensitization where because of that leaching of chrome, nickel, and iron, you get this cracking formation within these dog bone samples that we tested. And you get these carbides that form in the interstitial areas of those cracks. And as you can see here, the strength challenges are tremendous. Like you have this massive drop in tensile strength just because of this leaching occurrence. So again, in the solar world, this has been very concerning if we are going to fund tens, if not hundreds of millions of dollars in these large CSP power plants. Where is all this materials information important? Well, we've also been developing advanced molten salt valves and pumps. This is an advanced molten salt valve that we've been working with Flowserve and Kairos Power over the last 3.5 years, where we've put things like a heat pipe valve stem and an active thermal management system, which we call the STM, within the bonnet of a valve so you can minimize the thermal gradients and also create gradients where you need them for good operation and most importantly, O&M, something that isn't always talked about. And so we've been working with companies like ACT to put these sodium heat pipes within the valve so we can, and nitrogen gas or argon purge ports. So that way we can utilize these for both chloride salts, which we tested with Flowserve, and Flynac with Kairos. I should also mention we've come up with designs for either a bellows type seal or a quick change packing. So instead of having to actually cut out a valve or disconnect it from flange, you can actually disconnect the packing on the quick change packing and basically do your change outs within an hour. So that's a pretty big change whenever you're looking at O&M costs. This is also another development from that same project. In Villach, Austria at Flowserve, we developed a 750 degree chloride salt test loop. We've been able to successfully test our valves with about 1,000 actuations, and I think it's somewhere around about 1,000 hours of testing already in this test loop. We've tested these multi-material spiral wound gaskets where you basically have graphite spirals at the inner core and then thermoculite on the outer core. This has been able to satisfy an 11 bar pressure that is applied and without any leaks, at least thus far. We plan to continue testing with this system, which we also include Argonne, National Lab Nathaniel Hoyt's chemistry control sensor, and these more accurate, which we've found compared to like Jeffrin pressure sensors, Sporian microsystems pressure sensors, and flow sensors. There's a star pack design that's also a part of this valve that has 2 pressure sensors, and using that, we can actually now get pressure and flow at every valve. And that's part of what we are testing as part of the system. So you don't have to go out and buy an ultrasonic meter. All your flow control valves, now you can get pressure flow with all of this, including some controls. Kairos Power, we have an isothermal batch system. So we tested the chlorides in our test loop in Vlok, Austria, but we're also testing Flynac, where we can move the salt back and forth between these 2 tanks and still be able to test the CV values and the actuation cycles with our flow control valve. All of this research is wrapping up for both systems at the end of this calendar year, and we're planning to do freeze-thaw cycles on this valve at Kairos in Flynac. So there'll be a lot of really good and really interesting research coming in a number of publications. Another work I'm going to briefly touch on is the work by ORNL. They've been working on industrial tanks. In CSP systems, the diameter of these molten salt tanks can be as big as about 100 feet in diameter and about 70 to 80 feet tall. So there's a lot of thermal gradients. There's a lot of materials challenges that we find. And there are limitations that we found, such as the API code and standard, which for tanks is limited to only about 260 degrees C, because for petrochemical and some of the fossil fuel industry, that you don't really, I guess for some of their tanks, they don't go beyond that. And so there's been a lot of work by the Department of Energy SETO office to be looking at updating these codes and standards such as API. There's been a lot of failure mechanisms failures happening in many of the salt tanks in CSP, and a lot of lessons learned where there's been a lot of research funding going towards the national labs and companies such as JT Thorpe and Hatch and Jobe Industries to identify and try to overcome some of these challenges, such as local transient stresses that you can get in tanks, non-uniform thermal expansion, these sorts of things where you can get buckling on the base of these tanks, as well as on some of the joints on the edges. There's been a number of modeling CFD and other FEA models, as well as some other predictive models that have been developed in-house to look at the thermomechanical stresses in tanks. So, for example, there's been tank floor fabrication modeling. Typically, you get these panels, you weld them together on the base of the floor of a tank. And then you also have to consider what are the radius of curvature, the welds. You need to have a certain radius in some of these tanks. Some of these things are not always obvious, but whenever you're looking at thermomechanical stress, it's important that you do a good job modeling and understanding not just the welds on the bottom interior, but also at the interfaces with the vertical walls. So that's been something that's been ongoing with NREL, looking at the different stress regimes, and then also weld qualities and inspections whenever we're doing tank development. They've also been working on Lamosa. One of the takeaways that we found in the Gen3 program is that it's not enough to have an externally insulated tank, but utilizing an internally insulated tank, you're able to also create these nice thermal gradients that actually can improve the reliability overall of the tank. And also, one of the things that we found in industrial systems with these large tanks and pumps is sometimes you get these natural frequencies with long shafted pumps where they start to have these oscillatory effects that causes a sloshing. So you go back to Navier-Stokes and there's that sloshing term that makes a big difference now. And so now what we can do with these interline tanks is that actually can dampen some of that sloshing effect. It creates a nice thermal barrier and improves the reliability. Plus now you can use stainless steels on the outside of your tank walls, because by the time the salt gets to it, it's at a low enough temperature that you're not really getting into a lot of corrosion challenges. So we've been testing at NREL a large Lamosa tank with interline and actually been getting really good results. Again, those will be published soon. Lastly, I will touch on some of the work that Lewis talked about during his lightning round. We've worked with folks like Mark Anderson, University of Wisconsin-Madison on various projects. These are just a few selected ones in salt tribology, salt corrosion studies, pump development, and salt chemistry. So in tribology, as Lewis was talking about, there's been a lot of interest in understanding how bearings in the salt, unless you have a cantilever pump, you're going to have bearings in the salt. And that can have a lot of challenges whenever you're getting into galling, burnishing, and abrasion. So there's been some really good work by Wisconsin-Madison to look at this in collaboration with companies like Powdermet, developing Cermet materials and the like. They've also been able to develop a lot of different types of pumps and looking at different stages of the pumps, looking at thermal gradients, again, with the ternary chloride salt, since that's what the DOE SETO is interested in for this work. Also looking in the gas space and seeing how the interactions between the liquid phase and the vapor phase also interact with pumps. There's the magnetic bearing pump. Again, one of the key features of this is that it's inline. So you have a variety of applications you can look at. There was a lot of additive manufacturing that went into this. And some of the work that the DOE SETO has funded was look, what are the differences in corrosion for additive manufacturing versus casting versus forged? Like we'll say we found that casted materials can be a third the cost of forged materials, but there's a corrosion challenges that can occur. And with additive manufacturing, we sometimes even find that corrosion issues become even worse. And so this is also something that is still ongoing in research. And for their study, this is a really nice compact study that's looking at a variety of different things. And then there's been in situ optical absorption measurements. This has been also ongoing research, looking at a robust probe design for, again, looking at salt impurities, especially if you get any breaks in the system and you get any water entrainment where you get that reduction reactions, especially with the mag chloride. For that, I'd like to thank you for your time.
Thank you, Ken. We'll take a question.
Ed File from Exodus Energy. Have you talked to the resource guys, the ones that convert rocks into metal and stuff? Because they're building these tanks and stuff like that at 2500 C max. So they already know how to do a lot of this stuff.
Yeah, that's actually where a lot of the research started from the recent research for this. There were industrial partners, especially with industrial process heat, that were assessed when building some of these larger tanks. But there's also not good communication of information with some of the EPCs that ended up actually building the tanks. So there was some lessons learned of being able to utilize best practices. So that's also something the Department of Energy has been working with a gentleman by the name of Bruce Kelly to kind of lead that effort for industry, working with others like you mentioned.